All right, this is not too different than the one we just did. All right, so Sarah has got a block of wood and she puts it on the edge of a merry-go-round and she starts rotating it faster and faster and faster. And at some time, the block slips off and goes flying away from the merry-go-round. Okay, and our task here is to figure out what's that speed? How fast is it going to go flying? All right, then if we wanted to, we could turn it into a projectile problem. That would be fun. Okay, so start off with our sketch. Okay, just like normal. Here, here's my center. Okay, now we don't know how fast it's rotating. It's out here on the edge. Well, let's keep it still out here on the edge, and we know that distance right there it's 2.5 meters. We know that the mass of the block is 2.5 kilograms. And the coefficient of friction there for static friction is 0.55. Just like so, okay? And that's all we got. Okay, I'm going to put our target on there just so we don't forget. What we're actually looking for is how fast is it going to be going once it takes off? Okay. All right. So free body diagram here. All right. Let's think about our forces. So we know we've got some weight acting on it, like so. We know we have a normal force acting on it, like so. And then we know we have friction pushing in this way. Okay, so there's our friction. I'm going to go ahead and put our centripetal acceleration on here. Center seeking acceleration, centripetal. There we go. Okay, sketch, check. Free body diagram, check. Let's get to Newton's laws. So here we go. Let's use this color. Okay, so if we start with the y components. Okay, so we've seen this before. 0. So N is just the weight, which is mg. Okay, and let's look at the horizontal forces here. Okay, so our friction is to the left, and we have centripetal acceleration to the left. So I'm just going to go ahead and write that as F equals MAC, like so. Now the friction, okay, friction is less than or equal to mu times the normal force. Okay, so if I put that in over here, then I kind of like to do it like this, because I get, to be real honest with these inequalities, it can be tricky which way to do these things. So I kind of like to do it like this. The friction there is going to be less than or equal to, I want a different color though, less than or equal to mu times the normal force. Okay, that way I can just write down here mu times the normal force is greater than or equal to MAC, just like that. Okay. Now, for our particular case, this thing's going to go faster and faster and faster, which means the value of AC, all right, is going to get larger and larger and larger, okay, because MAC is m omega squared r. So the faster it goes, the bigger omega gets, okay, but then there's the limit, and this is the limit, okay, and the limit is going to be when these things are equal, okay. So if MAC goes bigger than that, we got a problem. It's going to go flying off. So this will be the last point at which it can stay put. Okay. All right. So I've got mu times the normal force, which is the weight, which is mg. And that's going to be m omega squared r. Now this is kind of cool. My m values are going to cancel out there. Okay, that's kind of neat. Oh, and you know what? I don't want to use the omega squared r configuration. I actually want to use v squared over r, like this. So I'm going to pop in here v squared over r. Okay, so I've got mu g is v squared over r. So when we do a little bit of algebra on this thing, rearrange it, I'm going to get the square root of mu gr. Okay, and we'll plug in some numbers. 0.55, 9.81 meters per second squared, and my radius is 2.5 meters, just like this. And after I calculate that, okay, I get 3.673 meters per second. And by the time I truncate that to 3 sig figs, I get 3.67 meters per second. Okay, let's go back and check out our units. I've got seconds squared, which becomes my seconds there. And I got meters times meters, which is meters squared, and gets me back to meters there. So my units check out too. Okay. All right. Now, all right, so we get 3.67, and that would be the point at which the block will slide. Okay, and since the coefficient of kinetic friction is lower than that for static, once it begins to slide, it's toast. It's gone. Okay, now, remember we've talked a lot about models, okay, and this is the most simple model we can have, and really it's actually not particularly accurate, because it's possible the block could, depending on how wide it is, how tall it is, it could flop over. So let me just kind of introduce this to you. We'll talk more about this kind of thing for those of you in engineering doing dynamics in the spring. So let me just take a quick look here. I just kind of want to give you an idea. So here's our block sitting on there, and I made it kind of tall. It's got a center of mass up here. And so the friction is acting down here like this. And you can see it's out of balance. And so if we think about a torque or a moment around the center of mass, all right, you can see that's going to want to try and rotate it this way. All right, now, once that block starts to tip up, all right, then the weight here is going to pull it back down. So I've got some competition in terms of the torque between the weight and the friction. So they each want to cause it to tip in different directions. Now, as long as we're below a certain threshold, then they can match each other and it's just fine. But if that centripetal force, if the friction rather becomes high enough, then that block's just gonna fall. Oh, I did the wrong way. It's just gonna fall right off of there. Okay, it's gonna tilt this way. But that's the kind of thing we can look at in the spring in dynamics. We need a few more tools. We can't do it here because we don't know the geometry of the object. All right, and it depends a lot on the geometry of the object. You can imagine a tall, skinny block is going to tilt over much more quickly than if it's like short and fat somehow. Okay, anyway, there we go. I'll be back with another one.